All right, welcome back, Science 7. This is another lesson from Unit C, which is heat and energy. And we were talking about energy. Just a little recalling, we are going back into the concept, something known as kilowatts and watts. Basically, and I didn't go through that in detail, watt is a unit. It is a unit to determine how much of power will happen for each of the electronic devices, including anything that involve with heating too. And even though power formulas and so on, you guys will learn about that in future science courses. But one thing that I want you to understand right now is power is a concept of comparing how much energy is produced or used per certain hours, which is energy goes on the top, and at the bottom, you have time. Energy is a concept of joule and kilojoule, which we use the capital letter J to find out joule. Joule is, well, it's another unit like watt over here. It shows the energy. Time can be, and this is where things are getting a little tricky, second or hour. And most of the house related product or any type of machinery, in fact, in any type of device like car even, it does use hours a lot. So if you look at each of those devices in home, the average American home use about 10,932 kilowatts, and can you see, per hour annually. Oven use 2.3, electric furnace, which is the one that is related to direct heat. So I'm going to emphasize that a little bit more. That's 10.5, which is about roughly times by 5 times of oven. Electric water heater is also the one that consumes quite a lot of energy. Clothes and dryer, refrigerator, dishwasher, everything basically use heat. And whether you like it or not, light produces heat too. So have that in your mind. So we must save our energy. We must use the resource in a sustainable way, and I'm going to highlight this sustainable obviously to ensure that we do not damage our environment and put our futures at risk. And in order to save our energy, I want you to put um, a term here. Can you put renewable energy? Renewable energy. Renewable energy is what we need to use. And we're going to talk about that in future. In 21st century, what is the best way you think we humanity use to produce the maximum yields of energy? What type of power plant is being developed right now? And the answer is this. We're basically building a sun. So it is an experimental tokamak nuclear fusion reactor. And nuclear fusion is a fancy way of saying you are making artificial sun because most of the planet and stars they actually undergo something called nuclear fusion. It is really really tough technology because the heat energy is so dangerous, and as you may notice, China, EU, India, Japan, Korea, Russia, and US are participants of that. Canada, I'm not too sure, but I'm pretty positive they pitch in some. All right, let's do one practical problem. I want you to take out a blank pieces of paper or science notebook because we are going to go through one more calculation example. But to be fair, it doesn't involve a lot of calculation. And I want you to copy this question down. Please put a pause button now. Once you copy, here's what's happening. Incandescent light bulb produces light for an hour using 40 watts of energy. CFL light bulb produces light for 2 hours using 28 watts of energy. Compare the performance of the light bulb. So we are comparing which one is more efficient light and use less energy. So here's something that I want to point it out first. When you try to compare, that means um, we are choosing the most efficient device. We have two. We have incandescent light bulb and we have CFL light bulb. And we are comparing these two. And obviously, the one that it should be considered most efficient, that means perform longer with less energy. So that means CFL light bulb is actually more efficient bulb. But I'm going to prove to you briefly. Incandescent light bulb, let's think about the calculation a little bit. So in previous one, it says when it comes to 40 watts of energy per hour, that's a fancy way of saying incandescent light bulb has 40 much of energy happening per hour. On the other hand, if I look at the other type of light bulb, it says 2 hours for 28, which is a fancy way of saying 14 watts in that case. So as you may notice, 14 versus 40, you do know that obviously 40 is more energy consumption, more energy use. So our 14 watts of energy that's happening for 2 hours, that is better performance having devices. So have that in your mind. All right, let's continue. So now we finish our chapter one, which is about the history perspective of how humanity had been using our heat as an energy source of energy. And now we're into a chapter two. This is more chemical related part or chemistry. Sorry. We're going to talk about how heat affects matter in multiple different ways. So let's start our very first part. In every single matter, we have three physical states of matter: solid, liquid, and gas. Know the fact that when I talk about solid, liquid, and gas, these three matter always exist for every single matter that you can think of. Every matter can have these forms. So for example, as you can see, we have water as an example. Solid form of water is obviously known as, I'm gonna change the color into blue. Solid form is ice. Ice is known as H2O solid. Liquid form is what we generally put it as water at room temperature, H2O liquid. Gas is the one that we call vapor, water vapor, and that's H2O gas. Similar like that, as you may notice, can you see that I put H2O as everything? The only thing that basically changed from my writing is what's followed by right after solid, liquid, gas. These guys are the only one that change. We call it physical state. What you actually observe, can touch, can feel the temperature, those kind of things. The property of water doesn't change. It just isn't having a solid format. So it doesn't move, it maintains its own shape, those kind of things, versus liquid, which can be transferred into different container, or gas, which can escape any of environment. Similarly, if you think about um, solid iron, iron use Fe solid. If you think about iron, you can apply a lot of heat and it's gonna turning into molten iron, which is Fe liquid. And technically, you can actually vaporize these guys into iron gas too, which I never seen in my life. But theoretically, if you raise up the heat, it is possible. So again, know the fact that the only thing that play a huge role is basically it seems like it's going off. Solid, liquid, gas, the physical state. Everything else about the chemical property, it's same. Iron is iron. Water is water. So let's go through this. I want you to pause the video to answer the following question. What are the observable differences between solid, liquid, and gas? Explain at least 3 differences for each. I want you to get things started. All right, let's get this started again. So what I'm going to do is I'm going to share some of my answer and I want you to compare with yours. The question asks you about write down 3 observable differences between solid, liquid, and gas. So I'm going to put each of them. When it comes to solid, as you can notice, the volume is fixed. That means think about square cube, ice cube. That doesn't change into anything else. Even if you try to change the shape will be broken into different fragments. So volume is fixed. On the other hand, when it comes to liquid, you can control the volume. So what I mean by that is it's kind of hard to say. Volume is fixed, but it is flexible. That means it can move around. Depends on the container size. You can control how the volume will look like, even though it is a fixed moment. When it comes to gas, volume changes. Volume is something that changes all the time when it comes to gas. And it actually changes depends on the pressure and temperature, which we're gonna get there. When it comes to solid, fixed motion. You rarely have any motion, in fact, when it comes to solid. Like ice doesn't move. But when it comes to liquid, more fluid motion. It can flow from one area to another. Gas has most movement. I'm just gonna erase this 3 water. The third one, solid, liquid, gas. Let's think about those. The third perspective I like to say is solid are very rigid and how can I say rigid and strong. That means you cannot change much about its structure. There you go. On the other hand, when it comes to liquid, those are more soft and mobile. And when it comes to gas, most weakest in terms of its strength. I mean, you cannot move it. You cannot fold a shape. Let's put it that way. And they escape a lot. So I have a hard time including in inside of a structure. So these are what I can share with you. I want you to look at this now. Heat energy and physical state. One thing that you need to understand is heat energy has a direction. It's go from hot object to cooler object. During that process, heat energy can be absorbed by the colder object, and when it comes to the other side of that coin, heat energy can be released by a hot matter. So think about the direction. It does not only go from one side to another, what happened afterward. So when heat is absorbed by a cooler object, here's what happened. Solid can turning into liquid. We call it melting. When it comes to next, liquid can turning into gas. We call it boiling. And those are happening because heat energy is absorbed. On the other hand, when heat energy is released, we call this gas to liquid, which is condensation, and liquid turning into solid, which is solidification. So, or freezing. I like to write those on your note. Pen, green. Solid turning into liquid, we call it melting. Liquid turning into gas, we call it boiling. Gas turning into liquid, we call it condensation. Liquid turning into solid, we call it freezing. Therefore, here's a little bit of a graph relationship. If we have a temperature on the y-axis, that's our vertical part over here, and the unit is degrees Celsius in Canada. And on the other hand, how much heat energy that is being provided, here's what happened. If it's solid, let's say ice, then temperature goes on and then ice will be heated up too. However, when it comes to solid turning into liquid, we call this as melting point. You will notice that there is not much of temperature change. But once we go with fully liquid, it's gonna boil up again. But again, there is a part where temperature doesn't change because heat is being absorbed, and that part is what we call boiling point. During these two stages, ladies and gentlemen, I want you to write one thing. Temp change is not observed. The reason being is because the the heat energy is being absorbed by every single matter that compose this water, or I guess I like to say ice as a first, then water, and it is turning into vapor. During that stage, absorption of energy is happening, and that's why the temperature change is not observable. You guys will learn about that as we go through more journey. And that's when we're going to finish our lesson for today.